Dr. Palash Padar, sir. The session
Okay.
is yes, sir. Please take it.
Okay. Thank you.
Good evening, everyone.
Good evening, everyone.
Now I'm going to talk on
Now I'm going to talk on magnesium, metalworking processes, alloys of magnesium, applications. Magnesium is the lightest structural element in the periodic table. It is 36% lighter than aluminum and 77% lighter than steel. Now the properties begins with physical properties, mechanical properties. The physical properties will include maybe viscosity, maybe thermal conductivity. It can be like for mechanical property, the UTS value, yield strength, all these are very important. The percentage elongation is calculated by reduction in area, okay, cross-sectional area. And the characterization may include several things like SEM, TEM, optical. Now, first, I'll begin with metalworking processes, then we'll come down to the real world of magnesium. The next. Metalworking processes are techniques used to shape metals into desired forms of other shape applying by mechanical forces, heat, or both. This process rely on the principles of material deformation, mechanics, and metallurgy. The fundamentals of metalworking processes includes direct compression, indirect compression, tension, bending, shearing. The direct compression means when you are applying load, the metal will flow, and the direction of the flowing of the material and the direction of the force on the same line. That means it is called direct compression. When the metal flow is perpendicular to the direction of applied force, then it will be called as a indirect compression. And tension means when the tensile load will be applied, that times metal deformation will take the by following the tension mode. And bending, when there will be bending moment on the material, the force will be applied accordingly. Shearing means when the metal will be elongated, then perpendicular to that the shear force will act on it. So these are the basic fundamental principles for metal working. The major working processes are metal working are rolling, forging, extrusion, and somewhat drawing also. The rolling is plastically deforming metals by passing it between two rolls. And forging basically means hammering. The principle basically means hammering. Hammering and the extrusion process are various. I'll go into details of all these. The rolling can be categorized into three parts basically: hot rolling, cold rolling, and warm rolling. Now, the hot rolling, the cast structure breaks down, homogeneity in the final product will obtain, lower energy requirement during rolling because flow stress requirement is very low. Crack development diminishes because at hot working temperature it is much more soft, and the force required will be very low. Whatever blowhole porosity, all those will be eliminated during hot rolling. Like that, blowholes porosity eliminates, ductility and toughness increases. The products are generally slabs, blooms, blades, strips, plates, sheets, rod, bars, stripes, pipes, rails, structural shapes will get. In cold loading, we'll see that strain hardening will take place. There, the strength and hardness reduces. the ductility, but strain and hardness will increase, obviously, for cold rolling. Because cold rolled annual cycle is given to impart some ductility to that material. Suppose it is deforming with very application of very high forces, during that time, if annual cycle is given, then its ductility, materials ductility will also increase. Products like sheets, foil strips, this can be produced through this cold rolling process. Forging, although cast structures break down, strength, toughness, ductility will increase, and it has the ability to withstand impact load, shock, vibration, and high fatigue resistance. Products like bolt, turbine rotor, entire airplane wing, automobile, crankshaft, connecting rod, these are produced through forging route. Extrusion, the cast structure breaks down, reduces cross-sectional area. High alloy steel, nickel-based alloys, and HCP metals. HCP means hexagonal close pack metals are usually extruded. Because those are having less number of slip systems, the HCP structure, that's it's around pyramidal and this slip plane, basal plane, along the basal plane, it will deform. So that's why for extrusion, this ACP material extrusion is very suitable. Like nickel-based superalloy, as I told, ACP metals like titanium, magnesium, whatever the magnesium rollability is there, the more the deformation is given by rolling, it will be difficult to roll, but easily you can get the extruded product of ACP metals like nickel, base superalloy, magnesium, then titanium base. All this you will get much more deformation by extrusion process. Then cylindrical bar, hollow tubes, angles, and so many other components can be extruded. Different channels can be extruded by extrusion process. And as I told that between hot rolling and cold rolling, there will be warm rolling also. It is in between that, because hot rolling is done above recrystallization temperature and cold rolling is done below recrystallization temperature. This metalworking processes, it is basically a plastic deformation process. Workpiece is subjected to a very high compressive stress, because there will be several rolls, maybe 2 high rolling mill, maybe 4 high, maybe 6 high, maybe 20 high centimeter mill. But when load is applied on the rolls for both sides, that time the deformation will take place on the workpiece itself, and we can see that workpiece is subjected to very high compressive stress. Hot rolling breaks down ingots, as I mentioned earlier, transforms it to bloom billet slabs. Cold rolling imparts increased mechanical strength, hardness, but reduces ductility. Major objective of rolling pertains to thickness reduction. Major aim is like that, but there will be a constancy of volume, except porosity, then some cracks. These are the exceptions. Reduction in mill power by small diameter work rolls. Suppose there is 4 high rolling mill. There will be 2 backup rolls and 2 working roll. Inside the working roll, the workpiece will be there. The workpiece will be deformed as the roll diameter relating to the system, in the point that the roll diameter increases. That means the rolling load also increases. But reduction in mill power by small diameter roll means if diameter reduces, diameter of the roll reduces, that time you require less load. Backup rolls support the smaller diameter working rolls. Those are the purpose for the backup rolls. The roll diameter, this rolling diameter, next. rolling load is the P, sigma is the applied stress, and this R is basically called the roll diameter. The rolling load increases at a rate greater than diameter to the power half. Deformation resistance of the material, this rolling variables is one of the important point, deformation resistance. What is the strength of the material? Depending on that, the rolling load will determine that how much load has to be given. If it is high strength is there, then load requirement will be very high, and it is very ductile, then load requirement will be very low. And friction between rolls and the workpiece. This mu is the coefficient of friction, it depends. And delta S max is the reduction. This is the original workpiece thickness, and this is the final thickness. Original thickness, final thickness. Left side is the original thickness, right side is the final thickness. So, in between how much deformation it is taking place, depending on that, the coefficient of friction with that roll diameter, it will relates to that delta S max equal to mu square equal to R. Presence of front tension and back tension. There are several rolling mills are there. There you can see there is a front tension by ETR, entry tension reel, and DTR also, delivery tension reels. This ETR and DTR, if it is applied, the load, so horizontal it is applied, then vertical load of the rolling mill itself, the rolling load will reduce a bit. So that is called the presence of front tension and back tension. Hot rolling is done above recalcitrant temperature. Recovery and recalcitrant takes place during deformation in hot rolling. Very large deformation are possible in hot rolling. It occurs at constant flow stress. Energy requirement is much less because it is done above recrystallization temperature. And here we can get large deformation, so large strain is also there. Next. Now see the hot rolling processes or stresses. What is the stress for hot rolling? This hot metal is coming from the furnace or from the converter. It is taken through a ladle and it is a continuous caster. Through the turndice, it will move and it will be taken as a one cutter, torch cutter will be there that will take out the slab, and the soaking pit will be here, it will be softened, and then it will go for the slabbing mill. Then it will go for the reheating furnace. There it will be preheated, and there is a scale breaker. The high speed jet water will be impinged on both surface of the slab, and then the scale lot of oxidation will take place. It will be removed and it will pass through roughing mill, a 4-high roughing mill. Then it will go to the hot strip mill. Then after hot strip mill, coils will be formed. Those coils will be taken. Then it will go to the finishing stands. Here step by step, initial thickness, final thickness, initial thickness, final thickness. Come forward, next. Initial thickness, final thickness, and it will be cooled section, and cooling will be taking place. And then finally we'll get plates, rail sections, strips. This formation will be taking place and it will be sold to the market. Next, cold rolling provides superior surface finish and dimensional tolerances. Energy requirement is very high. As I told, hot rolling takes very less amount of energy, where the cold rolling, the energy requirement is very high because it is in cold condition. Flow stress increases with degree of deformation. Here we can see two examples, cold rolling of copper strips. And right side we can see there is cold loading of brass strips. These are called the screw down system. Right side, this is called screw down system. Now we can see there is Sanjeev mill, 20 high Sanjeev mill. Why it is called 20 high Sanjeev mill? Because 20 rolls are involved in it. 20 rolls, A, B, C, D, these are called H, G, F, B, backup rolls. There is one roll centrally which is called intermediate idler roll on top, and one at the bottom, it is called idler roll. The star shaped four rolls, these are called drive rolls. Drive rolls. And primary intermediate roll is these two nearing to the work roll. Work roll is shown in the black color, and in between there will be strips. For any kind of cold rolling, it will be done through sensible mill, and it will give the much more surface finish. Very low thickness you can get it, around about 0.46 mm thickness you can get it for stainless steel, and this is called 20 high sensible mill. This is the real picture you can see from the side. This is explained. The intermediate rolls are these two are the intermediate rolls. Here is the work roll. So it is connected through the springs, and these are all the thrust bearing. It is called thrust bearing. It will be covered this area. Next. Now coming to the forging. Forgings are categorized into three parts: open die forging, closed die forging, and offset forging. Next, open die forging. Flat dies of simple shape, inexpensive dies. Dies are not so costly. Large object and less number of parts can be produced through this. Preform the workpiece for closed die forgings. For closed die forging, it will be preformed, means it will be prepared initially. Some intermediate shape has to be given. Wide range of sizes are available for this open die forging. There will be good strength characteristics for open die forging. Now there is a formula for open die forging. P is the load, sigma AK. P is the force or load. A is the forging projection area, sigma is the mean flow stress, K is a constant 0.8 to 0.2 R, where R is equal to H by 2L. H is the mean thickness of the deformation zone, L is the length of deformation zone. Now for closed die forging, relatively good utilization of material, good dimensional accuracy, high production rate, good reproducibility, generally better material property than open die forging, and it gives very good strength characteristics. Here also there is a force and stress, cross-sectional area, and constant formula P equal to sigma AK. And here we can see next. We can see these are the upper die, and there will be a bottom die, and in between there is the forging stock. So here the A is the cross section area, P equal to sigma AK will be applied for this relation also. Where K is a constant, its value nearly equal to 1.2 to 25 m, 2.5 for offsetting, 3 to 8 for closed die, simple shape, and 8 to 12 for complex shape. Next, please. This one is closed die forging, standard terminology for various features. You can see there is flash gutter, then parting line, and these are the external and internal draft angles. The upper part is called rib, central part is the web, and this junction is called fillet, and around this is the corner, and there is the trim line. Trim line for excess portion of the forging part. It will go inside the this is called flash, actually the excess part, and it will go inside the flash gutter. So it will, and it can be cut down. That will be shown later. Closed die forging also can be dies, blank, and force will be applied from the top, and flash will be removed from both the sides. Stages of closed die forging for solid round billet. Comparison of forging with or without flash. Here we can see left side, there is a upper die, there is a lower die. Inside that, there will be the billet, and there will be force will be applied, and finally we will get, there will be a flash generated here. And this part is forging is, there is completely flashless. This is called the upper punch, and this is called the die. So force will be applied from the top, and we can see both side, flash side and flashless side. So this is the start of stroke and this is the end of stroke. Trimming flash from a forced part. So there will be trimming die here. Thin material at the center is removed. You see, at the center there is a thin material, this side, and there is a stationary punch. So stationary punch, and from top, the punch will be pressed from the top, and there will be small thin material. Thin material definition for this material, it is called slug, SLUG, slug. And this is the flash will be removed outside. This is called the flash. After trimming, this flash will be removed. So it is before a stroke, this is after a stroke. There lies the difference. So different categories of flash gutter. See, you can see there is parallel type of flash gutter, there is conventional type of flash gutter. This is called conventional one. This is tapered open, there is tapered close. These types of flash gutters are the different terminology of this flash gutter system in the closed forging. So forging a connecting rod. So there will be initially it will be blank, after aging, then blocking, then finishing and trimming. This aging process you can see there is a bulging area of this blank, and fullering is called this one. So aging, fullering, and that will give the final blocking, and then after machining it will be finished product, and it will be called as a trimming, forging of connecting rod. Offsetting. Bar cross section increases by pressing or hammering. Simple shapes takes simple stages, whereas multiple shapes takes multiple stages. Components such as bolts, nuts, washers, collars, offsetting of a cylindrical billet. So this is called offsetting of a cylindrical billet. Here the barreling is taking place after application of the forces from the top. We can see there will be barreling at the central position. Next. Classification and characterization of forging machines. There will be force restricted machines like hydraulic presses, stroke restricted machines like mechanical presses, energy restricted machines like hammers and screw presses. This is the schematic of the hydraulic press. You can see it is a ram. Here the fluid will be pressed from the top, it will come down. Then again it will be flown from this bottom, it will be going up. By that way, forging operation will be taking place. This is called a schematic for the hydraulic press. There will be mechanical press. There is a eccentric shaft. This one is eccentric shaft, and this is called the flywheel. It will move. It will rotate, and this is called the connecting rod. And this is the frame, and the ram will move up and down as the eccentric shaft will rotate, and the forging will be taking place. Here is a flywheel in the screw press. You can see the rotary motion of this one, and it will rotate this one, and the screw will come down, and the ram will finally forge the material. So this is called screw press for friction drive. And it is forging hammers. This can be basically two types: gravity drop hammer and power drop hammer. These are the schematics. And forging these are two dies, upper die and lower die, and forming a stock. And ram is coming down. There will be two roller, and in between the roller, the board will come down. This is called board. And for power drop hammer, there will be reduction gear here. So it will up and down, and accordingly the pneumatic air will pass through this, and it will make forward and backward. the forging will be taking place by movement of the up and down movement of the RAM. Next. So in the metal structure as a overall view, we can see this is for the casting structure, and this is for the machining, and this is for the forging. This casting means there is no grain flow. And here we can see machining, the grain flow broken by the forging process, and it is called the machining process, and it is the final grain flow revealed from forging. So casting, this is the macro structure, and machining, this is the macro structure, and forging, this is the macro structure. So grain flow comparison. Now we'll go for the classification of metals in decreasing order of forgeability. So metals and alloys. Aluminum alloys, its forging temperature is 400 to 550 degrees centigrade. Magnesium alloys, you can see 250 to 350 degrees centigrade. Then copper alloys 600 to 900. Carbon and low alloy steel 850 to 1150. So to tungsten alloys, you can see 1200 to 1300 degrees centigrade. Next, please. Speed range of forging equipment. Hydraulic press, that speed is around 0.06 to 0.3. Mechanical press is 0.06 to 1.5. Screw press around 0.6 to 1.2. Gravity drop hammer, what I have shown you, that is 3.6 to 4.8 meter per second, and power drop hammer is 3.0 to 9.0 meter per second. Now I will come to broad categories of extrusion processes. Extrusion processes are direct extrusion, indirect extrusion, backward extrusion, impact extrusion, hydrostatic extrusion. These are all categorized like this. Extrusion forces are F equal to A naught K ln A naught by AF. A naught is the original cross-section area of the workpiece. AF is the final cross-section area of workpiece. K equal to small k equal to capital K epsilon to the power n divided by n plus 1. K is the strength coefficient and n is the strain hardening exponent. The direct extrusion can be explained as ram movement direction and metal flow directions are same. Ram and container bore diameter is same. See here, it is the ram diameter and the container bore diameter. It is same, and billet is inside it, and extruded it will be forwarded as the ram movement direction. So it is called direct extrusion process. Same to it, direct extrusion. Indirect extrusion, die is mounted on the bore of the ram. Metal flows opposite direction to the ram movement through the bore of the ram. And ram and container bore diameter is same, but ram is hollow. Ram is hollow. That means this ram from right side to left side, its movement will be left outward, but extrusion will take place on the right onward. So ram movement direction and ram movement direction and the extrusion direction is just opposite. So this is called indirect extrusion. Backward extrusion. Ram is smaller than container. Small ram diameter is smaller than the container inner diameter. Material is moved up from the ram container annulus. This is called annulus on top. So ram is moving like this, and the material will flow upward. Extrusion will take upward. So normally a heated billet is used in this case. So this is called backward extrusion. Now impact extrusion. Next, please. Extrusion is carried out at higher velocity and mass lower temperature. Principle is similar to the backward extrusion. The container is made as short as possible because extruded product usually need not supporting after extrusion. You see, there is no support on top. Top there is no support. Extrusion will take place. So this is called impact extrusion. Hydrostatic extrusion is that metal is surrounded by a working fluid which is pressurized to give the extrusion force. At the left side, there is pressurizing ram, and inside that right side there will be a fluid, maybe hydraulic oil, and there is billet right side, and it will be extruded along the direction of the pressing ram. So this is called hydrostatic extrusion. Metal is surrounded by a working fluid which is pressurized to give the extrusion force. This is the principle. Extrusion basically means blank, then die, then final product. Now I will come to the world of magnesium. Introduction, characterization of base metal, alloying elements, alloying apex, alloys nomenclature, types of alloys, and then finally references. Introduction. The great chemical stability. Ease of machinability and fabrication. It is very lightweight, environmental friendly. As I mentioned in initial time that it is 36% lighter than aluminum and 77% lighter than steel. Used for structural application primarily in aircraft and missile industries, automobile also obviously. High thermal conductivity tensile strength is around 228 to 290 MPa. Heat resistance up to 450 degrees centigrade. Oxidation resistance up to 500 degrees centigrade. Oxidation resistance basically from the experience point of view I can say up to 350 degrees centigrade it doesn't oxidize much, but above 350 degrees centigrade it will oxidize vigorously. Characterization of base metal. It is 8th most abundant metal, 2% of earth crust, cheapest and lightest metal, 3rd most plentiful element dissolved in sea water, found in over 60 minerals, among them dolomite, magnesite, brucite, carnallite, and so on. It forms alloys, but use has been limited by its tendency to corrode, creep, and high temperature and combust. But nowadays, the high temperature creep resistance material are getting produced. We also have developed in our NML high temperature creep resistance material for magnesium alloys. And the alloying elements like aluminum, manganese, zinc, within magnesium, these can be added zirconium, thorium, tin, beryllium, calcium, cerium, copper, and so on and so forth. Addition of aluminum increases hardness and strength, it reduces ductility. But if aluminum is greater than 13%, that time material becomes too brittle because inside the metal structure, aluminum, magnesium structure, there will be a phase which is very, very brittle. That is called Ng17Al12, which is an intermediate. It's not an alloy. Probably everybody understands the difference between alloy and intermetallics. Addition of manganese increases corrosion resistance. To improve corrosion resistance under saline condition, 1 to 2% zinc is added. Zirconium refines grain size and gravity casting, not combined with aluminum, because when zirconium will be added to magnesium, then aluminum cannot be added because it forms unnecessary undesirable intermetallics. Tin improves castability. Tin is a metal which is having melting point 240 degrees centigrade, and it is very essential. If it goes to the magnesium metal, it will be forming Mg2SN phase, which is having around 770 degrees centigrade melting point, which is the intermetallic Mg2SN. Aluminum, zinc, zirconium, thorium promote precipitation hardening inside magnesium. Copper increases both room and high temperature strain. Next. Nomenclature. All this nomenclature I will be coming on the later stage of this presentation. Example, the AZ31B H224. Initial these two, A for aluminum, Z for zinc. That means 3 for 3% aluminum, 1 for 1% zinc. B is generally ASTM standard, sometimes B, E, D, all these things are used because of some purity levels concerns is also there. And this is the heat treated condition like partial annealed. The H2 is called partial annealed. And there will be T5, T4, T6, several treatments will be there for the subsequent heat treatment. So this is the first part of the AZ series and its T6 treatment. T6 basically the as cast, then T4 treatment will be there, then it will be aged. Artificially it will be aged, then that will call T6. And now I am coming to direct point that this nomenclature for magnesium alloy system, A is meaning as aluminum, B is for bismuth, C is for copper, D indicates cadmium, E for rare earth, F for iron, G for magnesium, H for thorium, J for strontium, K for zirconium, L for lithium, M for manganese, N for nickel, P for lead, Q for silver, R for chromium, S for silicon, T for tin, Y for antimony, or sometimes yttrium, W or Y can be used, Z for zinc. Thermally treated to produce stable tempers other than OH, ZF. These are the temper. Subdivisions of temper means this T1 to T10. All this temper can be given to the magnesium alloy system. Cooled and naturally aged, T1, T3, solution heat treated and cold water. T4 is for solution heat treated. T5 is for cooled and artificially aged only. T6 is called solution heat treated and artificially aged. T7 is called solution heat treated and stabilized. T8 is called solution heat treated, cold worked and artificially aged. T9 is called solution heat treated, artificially aged and cold worked. T10 is called cooled, artificially aged and cold worked. This is magnesium, aluminum, zinc, common types of heat treatable alloys. Artificial or natural aging causes increase in yield strength, ductility of the alloy decreases due to the heat treatment. Lightweight and highly corrosion resistant, it is manufactured in various ratios. Suppose magnesium 93% magnesium, 6% aluminum, 1% zinc. It is called AZ61 A. Similarly, aluminum zinc, it can be categorized like that. Small amounts of zirconium, manganese, chromium may be added to obtain fine grain structure before heat treatment. Corrosion resistance is good in the alloy containing small amount of copper. That means copper gives corrosion resistance. Used in various aircraft structures, forgings, extrusions, making sheets and all, manufacturing hydraulic equipments. Magnesium, zinc, rare earth, and zirconium alloys, most widely used alloys for sand casting. There are several kind of casting processes, but you see the most widely used alloys for sand casting is used magnesium, zinc, rare earth combination with zirconium. Rare earth is added to improve castability. Complex castings can be made with virtually no microporosity. Retain mechanical properties up to temperature of around 150 degrees centigrade. Used in gearbox casting, jet engines, etc. Then magnesium zirconium alloys containing silver. Improved high temperature like 200 degrees centigrade properties compared to magnesium zinc rare earth zirconium alloy. Silver is the main strengthening element. Common alloy contains 2.5% silver. Rare earth elements added like this neodymium, plasmodium, cerium, lanthanum, didymium, uh, your samarium, all these elements and more elements can be added. Sometimes scandium also can be added. Uses of aerospace gearbox, engine castings requiring high temperature performances. Magnesium, zirconium alloys containing yttrium, improved mechanical properties at high temperature compared to other magnesium alloys. Considered as alternative to thorium containing alloys. Very high resistance to corrosion than other magnesium alloys. This yttrium and zirconium is providing that facility for the magnesium alloys. Uses alternative to aluminum alloys in racing cars for large engine casting. Many application in aerospace industry due to its combination of strength, ductility, and corrosion resistance. Next, please. This is on electron metal. This was developed by British company Magnesium Electron Limited, one of the most famous alloys of magnesium. 0 to 9.5% alloying elements. Composition says aluminum less than 9.5%, yttrium 5.25%, neodymium 2.7%, silver 2.5%, GD, that is called one of the rare earth, gadolinium 1.3%, zinc 0.9%, zirconium 0.6%, manganese 0.5%, and other rare earth elements. Varying composition, varying variations in properties. Usually, light specific gravity, its specific gravity comes around 1.8 gram per cc. Good castability because of low oxidation properties. Due to relatively low density of magnesium, the alloy variants have different aircraft and motor racing applications. You can see the wheel. It can be wheel rim. It can be made of this alloy. Then another interesting alloy is Magnox, mainly composed of magnesium and a small amount of aluminum. Abbreviation, we can see the magnesium, M for magnesium, non, N, and oxidizing. The first letter of all these three gives Magnox. It has many industrial applications. Magnox is used in cladding, unenriched uranium metal fuel to container fission products in nuclear reactors, low neutron capture cross section, limits the maximum temperature of the plant to 360 degrees centigrade, reacts with water, preventing the long-term storage of fuel. The MACTHOR is another development. Common name of range of this magnesium alloy containing thorium. Also contains manganese and zinc. Names are given by the two letters followed by two numbers. HM31, 3% thorium and 1% manganese. Lightweight, it is high strength, having high creep resistance at 350 degrees centigrade. Up to 350 degrees centigrade, it is having very high creep resistance. Low melting point, rapid oxidation, several aerospace applications was used in engine construction and missiles and drones, for example, Bomark missile, but no longer used due to radioactivity of thorium. Metal 112, that is called alloy of magnesium and aluminum, developed by Samsung in 2018. This is highly lightweight and durable. Magnesium is lighter than aluminum and stronger per unit volume at the same time. So thus, magnesium is also termed as metal for the future. Now we'll see the mechanical microstructural. We have to see microstructural features, properties, and application of magnesium alloys. So you see, magnesium can be produced in several ways. Like it can be produced through PGN process, it can be through magneton process, it can be through electrolytic process. That is called electrolysis. So we found that 2.8% in the sea water and other forms, that is dolomite, magnesite, and carnallite. Magnesium with 99.8% purity are readily available but rarely used in this stage of engineering applications. The applications you can see here, the cam and mobile phones bodies, the magnesium side panels and alloyed wheels, gearbox housing, aerospace application and so on. Already we discussed about some physical properties, mechanical properties. The crystal structure obviously is a ACP structure, hexagonal closed stack structure. Density is 1.74 gram per cm and melting point is 650 degrees centigrade. Alloyed with aluminum, zinc, thorium, rare earth metals to produce alloy with high strength and weight ratios. To form compounds with negative valence ions due to strong electropositive rather than solid solution. It has a high tendency to form intermediate, form some kind of intermediate formation there. The solid solution. Solid solution means what? Solid solution means there will be a homogeneous solution with more than one or two alloying elements of crystalline solid that will form a single phase of material. That is called solid solution. Solid solution can be of two types. Basically, that is called interstitial solid solution or substitutional solid solution. Interstitial solid solution is magnesium. You can see the interstitial solid. Substitutional solid solution, suppose there will be a 22 karat gold. You can see that inside gold there will be some atom that will take place of like copper or silver. So it replaces the gold atoms. So it is called the substitutional solution. These are the examples. Not readily physically at room temperature due to discipline because number of system. Cast magnesium alloy dominate 85 to 90% of all magnesium alloy with magnesium aluminum system being the most.
Hello, sir. సార్ ఉన్నాడు. ఉన్నాడు. ఆయన పైన పైన మ్యూట్లో ఉన్నారు.
Hello.
హలో సార్.
Hello.
ఏ వెనక్కి వెళ్ళరా. హలో సార్.
Hello.
సార్ యూఆర్ ఆడిబుల్ సార్. యూఆర్ ఆడిబుల్.
Okay. I'm continuing.
Yes, sir. Yeah, you're audible, sir. Please.
Okay, thank you very much. Magnesium alloy, 85% to 90% of all magnesium alloy products with magnesium aluminum zinc system being the most widely used. Low strength and corrosion resistance is also low. Easily level but burning takes place. This now classification, the SC system designated by the two capital letters you see, all the aluminum, copper, cadmium. Next, the magnesium contains 9% for AZ92A. The magnesium alloy contains 9% aluminum and 28% of zinc. The QE22A86 means the silver is 2% and for ARR is 2% is plus points and artificial condition. The commercial magnesium aluminum based alloys, magnesium based alloys, magnesium aluminum based alloys phase diagram is magnesium aluminum. You see, 12.7% is the highest solid solubility of aluminum and corrosion resistance. Maximum solid solubility is 12.7%. As 437 degrees centigrade. It decreases to 3.8%. 400 degrees Fahrenheit. Group includes magnesium, aluminum, zinc, AZ63, AZ92. The microstructure of AZ92 is explained here. The structure in sandcast condition shows a network of M17A. This is the intermediate phase. However, most of the activity separated. The sigma phase has joined the primary sigma grain and the compound as a white network. In white network is alpha magnesium. Cooling and subsequently artificial aging can cause precipitation of the compound as fine particle within the grain. You see the fine particles, this precipitates. Fine particle precipitates of intermediate. This is the alpha magnesium. Junction point, it will alpha. Portion is called the beta phase, M17Al12. The wrought aluminum alloy like M1A, 1 for manganese is basically low cost, low strength, corrosion resistance, and hot formability. AZ3 was with low calcium content is widely used for magnesium photo engraving sheet. 6-on-A AZ80A has good strength and ductility. Because little low aluminum is there. So for wrought purpose, actually this aluminum should be little low, like it is having a 9% to form less amount of Mg17Al12 those intermediates, because those are very brit. To avoid little lesser of this intermediate, this deformation process or the mechanical working, or you can say the wrought products requires these specialized alloys. So these are things as AZ91D, AS4142, and several permanent casting alloys are also AZ81, AZ91, and AZ92A, and these are the several applications of automobile wheels, automobile housings, refrigerators, parts for cars, sand castings requiring good room temperature, strength, ductility, sand and permanent mold castings requiring room temperature, strength, and ductility. Mechanical properties of magnesium aluminum based alloys. We can see the tensile strength of around 220 MPa and yield strength 131, and percentage elevation is 8% for AM6 alloy, whereas 2A alloy at T6 condition
we can see there is only 1% elongation, whereas 24 MPa is 0.2% yield strength, and 234 is. Hello. Hello.
Sir, you're
Hello.
audible. Yes, sir. Yes, sir.
Am I audible?
Yeah, you're audible now, sir.
Okay. Essentially, the magnesium zinc, zirconium, and magnesium zinc thorium casting alloys. This magnesium zinc based alloys. Zirconium is added for grain refinement purpose, so to increase the mechanical properties. Zinc controlling is important as it causes micro porosity inside the casting and hot cracks. So thorium and rare earth metal is added with effect on mechanical properties. Jet K51A, say for instance, zinc K for zirconium. And the higher tensile strength is, it shows the ductility of any magnesium casting alloys is increasing. Magnesium rich solution, this white portion is solution. And at the boundary, grain boundary, we can see the compound of magnesium, thorium, and zinc. The chemical composition, application, mechanical properties of magnesium zinc based alloys. For GK1 around 4.6% ranges to 5% or it's around 0.7% zirconium. So it's a variable range of compositions for different alloys. And with tell properties for GK51A is UTS of 234 MPa and yield strength of 35 MPa and 5% elongation. And likewise, the JD means in the rare earth system 6, it is showing as condition it is 5% nucleation and 186 MPa and 275 MPa and 16 MPa. Magnesium rare earth cell includes magnesium rare earth, zirconium alloys, magnesium rare earth, zinc alloys. By adding of rare earth elements, we get temperature properties. So these alloys are suitable up to 40 degrees centigrade temperature. Magnesium, magnesium, this alpha white region is the alpha magnesium, and beside that green board magnesium is solid solution, and the depleted zone we can see this is called eutectic alpha magnesium, and at the boundary there will be lot of intermediate. Magnesium thorium based alloys include magnesium thorium, zirconium, magnesium thorium, improved temperature properties, short time elevated temperature under high stress, HZ3 to a long time stress application. The magnesium casting primarily used for aerospace application due to lightweight. Magnesium silver rare earth alloys QV22 has been used for aerospace application, that is landing gearbox housings. Magnesium yttrium rare earth alloys, that is WE43, has been developed for improved elevated temperature tensile properties. Coating of magnesium alloys. Advantages of forced magnesium components compared to used die-cast magnesium parts. The forged alloys shows excellent strength, especially with the fibers to the main loading direction. Very good property for pressure seal components because of a forging process in preventing a porous microstructure. Properties of forged magnesium. As compared to the as-cast magnesium wheels, 5-10% weight savings, identical design can be assured, and for aluminum forged wheels also, so magnesium wheels is a little costlier as compared to this aluminum. Joining of magnesium alloys, like arc welding, say for instance TIG welding, tungsten inert gas welding, or MIG welding, metal inert gas welding, then laser beam welding, electron welding, diffusion welding, friction welding, that is called friction stir maybe, and that is called actually solid state welding process, spot welding, which is basically a resistance welding process. Suppose for aluminum, basically spot weld should not take place because it's having high electrical conductivity, so resistance is very poor. Copper is also difficult. Magnesium spot welding is possible. Engineering design with alloys. Advantages: ability to die cast at high productivity rate, good creep resistance, high damping capacity due to ability to absorb energy elastically, high thermal conductivity permitting rapid heat dissipation, good machinability, easy gas shielded arc welded. Disadvantages: high tendency to galvanic corrosion with dissimilar metals or electrolyte or any other sea water condition, difficult to deform by cold working because of excessive structure. Thank you very much. If any question, highly welcome.
Thank you, sir. Participants, if you have any queries, questions, yep, you can ask now.
Hello, sir.
Hello.
Sir, I'm Mayur Sir from BIT Baldarpur. Sir, what are the major challenges in improving the strength and corrosion resistance of magnesium alloy for a practical industrial application?
Strength and corrosion.
Yeah.
For corrosion studies, alloying additions are being done nowadays. Alloying additions. This alloying additions.
Okay.
Like
Alloying element addition.
alloying element additions. Say for instance, tin, then your strontium, then silicon. Several alloying additions are there. For strength properties, also different TAS alloys are there nowadays, newly developed TAS alloys, and that is based on your Japan and starting your South Korea. They have started.
Okay, sir.
Thank you. Any more questions, please?
Sir, there is a question from participant called Vipin V. Sir, what are the current research gaps need to be addressed in the areas of magnesium alloys?
We need to develop high temperature magnesium alloys. Nowadays, thrust is on that. Because you see the automobile engine blocks, lot of efforts has been given.
Sir, hello, sir. Dear participants, there is a
Hello.
network issue. Yeah, sir has
Hello.
come. Yes, sir. Sir, now you are audible, sir.
Yeah. Then.
Sir, there's a small query that what are the present research gaps that are available in this area, sir? That is just the question that was asked.
Question is what the?
Current research gaps need to be addressed in the area of magnesium alloys.
Research gaps, basically, there are several directions for high temperature magnesium is one point. Another point is we need to develop some novel alloys, novel magnesium alloys.
Okay, sir.
Which
Dear
is
part- yes, sir. Please.
through alloy designing. Research are starting.
Okay. Dear participants, any more questions? Sir, there is a question. What sort of forging practices are used for magnesium, as it is hexagonally closed package structure, difficult to deform because of only 3 slip planes, and it is strain rate sensitive too. If we
Yeah,
go
yeah.
for high temperature die forging or isothermal forming, how the oxidation restricted? That's a question, sir.
That's a very good question. Actually, closed die forging can be made because it's just after aluminum. Its forgeability is just after aluminum.
Hello, sir.
Hello.
Sir.
Yeah.
There is one more question, sir. Is magnesium alloys currently made using metal additive manufacturing?
But that is in powder form, no?
Yes, sir.
That is in powder form.
Okay, sir.
Okay.
So thank you for your nice session, sir. So we will be collaborating more with the research aspects in near future. Thank you for sparing a lot of time for us, being a so busy person in the present scenario. Thanks a lot, sir. And
Welcome.
we'll be, yes, sir. Thank you. Thanks a lot, sir. Thank you. Dear participants, there is a 5 minutes break. Then we will start the next session by G. Rajesh. The session will be on industrial FEA. So once sir joins, we'll get back to you. There's a just 5 minutes break. Please refresh yourselves. Thank you.